Hey guys, um, this video will be about composite materials. But before that, let's say thanks for sending in your homeworks. I'm going to start taking a look at those today. I'll also be posting another homework set for the rest of covering the rest of Callister text. So that will be covering through Friday. And then I think I mentioned before, we'll have a short couple lessons about material selection. That material will not be testable, and I put it in the middle of the two texts to give us a buffer after we've finished all the new material and before we take the midterm to give some time to get through all of that before do homework problems, turn them in, ask your questions, those sorts of things. As always, any questions, please contact me. Put a comment in the Teams discussion, or email me, or text me, or however you'd like. So I'm going to go ahead and switch over. Give me a minute here to the notes so we can talk about composite materials. Now, composite materials here are covered towards the end because they're a combination of materials we've already talked about. And so a lot of what we've talked about previously will apply to composites in a way. But composite materials came about because as we've seen, looking at classes of materials individually, they have strengths and weaknesses. And if you need for your application a material that has properties that are characteristic of different classes of materials, a composite is an attempt to combine those properties, combine those two different types of materials into one material and potentially get a better combination of properties than you may have been able to get from any one class of materials by themselves. You essentially are able, to a certain extent, to combine the pros of multiple material classes and compensate for disadvantages of any one class of material. So this is what's meant by the principle of combined action. So you're putting these together, and they are compensating for one another essentially. And so when we have a composite, this is evident from looking at, say, the microstructure, or looking closely at the composite material, because it's made of multiple phases. And we've talked about phases before, as in, perlite is made of ferrite and cementite. Those are different phases. That's true. And so you have that microstructure phases. You also might say, well, what about a material like wood? If I look at the grain of wood, it looks like there's multiple phases, and if you look at it, on the microscopic level, you'd have cellulose and lignin, and neither one of those materials is considered to be a composite, because by definition, composite materials are only artificial structures. So yes, perlite and wood, they do have multiple phases that have different properties, but they are not, the size and shape and distribution of those phases is not a planned, artificially made material. We can tailor the conditions under which perlite forms but we don't say, one particle of cementate goes here and another goes here, the way you do when you make a composite. Composite materials, all of the examples we'll talk about in this lecture generally have two components. You have your matrix and then some dispersed phase. And this can be, as we'll see, a particle of varying sizes, or a whisker, or a wire, or a fiber. It's just a second phase that has, is made of discontinuous particles or discontinuous elements. And so they have a defined size and shape and a distribution, and also an orientation. So you can, in certain composites, carefully orient your dispersed phase or your reinforcement to be aligned with one another and all in one direction. And that gives you anisotropic properties for your material, which, depending how you make your part, can be used to your advantage. The types of composites are summarized well in this sort of tree diagram here. And you have three major classes of composites. There's particle reinforced, fiber reinforced, and then structural. Like it sounds, particle and fiber reinforcement are reinforced by particles and fibers. Within the particle, you can have different sizes and distributions of the fibers, the particles. And for the fiber reinforcements, the key thing here is alignment of all of the different fibers, and also the relative length of these fibers. If they are a very long fiber, potentially expanding the full length of the part even, then you would say they're continuous versus discontinuous, where you would have shorter fibers that don't span the length of the part. Structural composites are kind of, in a way, a composite of composites, in that you take composite materials and orient them and combine them to make a part. And we'll talk about a couple of examples there. Okay, so kind of looking at at these different categories kind of one at a time here. We'll start with the particle reinforcement. As I mentioned, particle reinforced composites, you can have different sizes of the particles, and the size scale of the particles determines how it behaves. So you have the large particles, then you're not talking about particle matrix interactions, really. Right? You don't really have, say, a disruption or lattice strain. It's more like a grain boundary, where you would have an interface between the particle and the matrix. And so this is not really considered to be atomic, because it's not like an atom in a crystal matrix that is producing lattice strain and strengthening the material that way. You have a bond that exists between the matrix and the particle. And so the load that is borne by that material is shared by the particle, and through this interface, through this strong bonding. If you have a much smaller particle, then you can have what's called dispersion strengthened material, where you have a very fine dispersion of these very fine particles, and these act more like a precipitate, perhaps, that you might get through age hardening, like an aluminum alloy, for instance, precipitation hardening, where the particles are so small that they get much closer to disrupting the dislocation motion, perhaps through the material on an atomic level, rather than the large particle, where it's sort of bearing the load itself. And so there, the critical thing is the size of the particle that's being distributed throughout the material, the reinforcement particle. And when you go to calculate properties, for example, say modulus, Young's modulus here, a common rule, especially for particle reinforcement, is to use what's called the rule of mixtures. Essentially, it is what you would think. It's that if you have a certain volume percent of matrix and particles, then your resulting property would be your resulting matrix would be some combination of the elastic modulus of the matrix and the particle that will be weighted by the amount of that phase that there is, right? So if you were to have, 50-50, for example, then it would be, the average of the modulus for the matrix and the modulus of the particle, which, intuitively kind of makes sense. If you were to go, and if you go to both extremes, you basically just get a pure material which has the properties of that pure material. This is often used as sort of the upper bound, right? So you'd say if I mix these together, the best I can do is to have kind of the average property depending upon how much of each that I have. Now remember, this is kind of an idealized case because the transferring the load between these particles is going to depend on the bond at the interface, right? And so if that bond is very strong, right, then they could share it very efficiently, and you would get, the best case scenario would be this line here, this equation. This first equation is giving the red line here in this figure on the right. But you may not have the bonding between the phases necessary to share the load as efficiently, right? So you may actually have somewhat less than what you would predict from the rule of mixtures, and so another equation is used to define kind of a lower bound where you have the similar to the rule of mixtures, right? Except you're kind of swapping the volume of the components here in the denominator. If you look at the form of this equation, and what you get is this nonlinear line here that forms this lower bound. And if you were to do some materials testing with these composite materials, right, you find that there is scatter, right? Just like we're accustomed to see in mechanical testing. We're not going to test. You could take the same sample from the same lot in the same conditions and test it, right? And there is a certain amount of randomness due to inherent flaws that have a random distribution and random variables like how the sample is prepared or how it's mounted. All of those things still apply, and so we see here that we get some scatter when we test our data. We test our samples, and but at least in this data set, right, it falls nicely between this upper and lower bound, which kind of gives you a range of the properties that you can expect. Okay, so some examples of large particle composite materials. Two here are a cermet material, so this would be a ceramic particle in a metal matrix. Example being, say, tungsten carbide or titanium carbide particles dispersed in a cobalt or nickel matrix, right? So if you have a metal matrix, right, you obviously need a particle that has a higher melting point so that it can be dispersed in the molten metal without melting itself. And these ceramics, or the cermet composites, because they have a high loading of this very hard particle, make great cutting tools. And the particles, since they're ceramic materials, tend to be brittle, and so they, are the properties of those materials, right? You would expect them to be hard but brittle and prone to fracture. But if you have all of these tiny particles in a metal matrix, then you don't have the same problem with brittle fracture because they're basically already in teeny tiny pieces. And if they continue to break further while you have other particles nearby, you're not going to have a crack propagate through the entire material. Right? In fact, a crack has to go from particle to particle through the metal matrix. Metals to form and give it some fracture toughness. So here you see an example of how you get the really high hardness of these carbide particles, but with the fracture toughness, say, of a metal, to make a very hard, long-lasting cutting tool. And the second example would be carbon black. We covered polymers in the last two lectures, and we mentioned elastomers and how rubber is an elastomer and it is toughened by vulcanization, which is the addition of sulfur to form those crosslinks between the polymer chains, and you actually get an enhancement of the rubber in tires by adding in carbon black. So carbon black is very fine particles of carbon, and they're added in a fairly high percentage, 15 to 30% or so, and you get an enhancement of the wear resistance of the material due to the interaction of these carbon particles with the rubber polymer chains here, and this would be the special interaction is at a very small scale. I mean, if you look at the length scales of these two micrographs here, you see that the cermets, we're talking 100 microns. For the carbon black, we're looking at 100 nanometers. So this is 1,000 times higher magnification, and so we kind of have, we're getting much closer to interacting on an atomic level with the carbon black than with the cermet. Other examples is concrete. So concrete, we talked about in the sense of ceramic materials of processing, about how you have that chemical reaction, the hydration of the cement to solidify concrete as a ceramic material, right? Since you can't cast it or form it. And we didn't mention that it's a composite material, but it is, right? You have a combination of different materials, different phases, right? You've got your cement, sand, gravel, water, and so obviously, having a good strong concrete is going to be dependent upon mixing those components in the right proportions, to the right degree, right, with the right amount of water, having clean sand, clean gravel, so that you can get a good strong bond at the interface between those particles by the matrix, which ends up being a mixture of the cement and the smaller particles filling in the gaps between the larger aggregate. You can take concrete, if you consider that to be a composite material, you can actually take it a step further, right, and add in not only different types of ceramic materials, but actually another class of materials in the fact that in the reinforcement. So you can add in rebar or metal mesh to address the pore tensile strength of concrete and give it a little more resistance to thermal cycling and the cracking associated with that. Steel makes a good match, not only because of its ubiquity, its what's the word? The fact that you can get it relatively cheaply, its availability, but it also has a similar expansion rate as the concrete, which keeps it from disrupting the interface from different ratios, different coefficients of thermal expansion over time. Sometimes the reinforced concrete is pre-stressed, meaning the reinforcement is put under tension, and then you pour the concrete, let it cure, and then you can release the tension, and what that will do is it will put a compressive stress onto the concrete from basically from within, and this puts it under tension, which we've seen before in things like surface carburization and in shot painting, or if you have a brittle material and you can somehow, and you see it in tempered glass too, you can somehow put a compressive strain on a ceramic material, that residual compressive strain will act to push cracks closed as they're forming. And so pre-stressing and reinforcing concrete can do a similar thing. Okay, so moving on to dispersion strengthened examples. I don't have as much information here. I already mentioned that the idea here is similar to precipitation hardening, right? And it's kind of, I guess, in the middle here, because precipitation hardening is, if you remember, it is the formation of a second phase within a first phase after the fact. So if you have a material system that has an increasing solubility limit with temperature, then you can dissolve one element in another at a high temperature, and then when you quench it, you create a supersaturated solution, a solid solution, and then if there's enough thermal energy available, then the atoms that are supersaturated in that solid solution will come out, will coalesce and form a precipitate. And this happens at a very small scale. And so this dispersion strengthened examples, it's the same type of dislocation, motion, disruption of the matrix material, but it's not quite as effective because it's not at an atomic scale. So it's kind of in between something like a precipitation hardened alloy and what we talked about here with the particle reinforcements, right? We kind of have a really small particle which kind of, it works kind of, in between. And so some examples that Callister cites are thorium oxide particles dispersed in nickel, and alumina particles in an aluminum matrix. And the key there is just that the particles are really small. Okay, so moving on to fiber reinforcement. So fibers are characterized by having length that is longer than the width, right? So that it has a high aspect ratio. And the goal here, in addition, the goal here is to combine strength and low density. So again, composite material. If you want strength, go with a steel. Steels are dense, they're heavy, and so what we're doing with fiber reinforced composite is trying to get the strength of steel, the lightness, say, of polymer. And so by adding these fibers, one of the key things is that the fibers are long enough to be an efficient reinforcement. Just like with the particles, we're relying on the bond between the matrix and the fiber. And so for that bond to develop, you need to have a certain length of fiber. As is shown here in this diagram here, near the ends of a fiber, you have the stress increasing, right, as there is more surface area for the bond to develop, and so there's a minimum kind of length necessary to fully develop that bonding, and so if you're below this critical length, then you never actually get the maximum applied load, the maximum development of this interfacial bond. And if you have a fiber that is longer than this critical length, right, then you have a good proportion of the fiber length where you have this maximum applied load, right? And so it is beneficial to have as long a fiber as possible because you have a higher ratio of maximum applied load to this bond development region near the ends of the fibers. And the magnitude of this critical length is dependent on the properties of the fiber and the matrix. So you'd have the fiber tensile strength and the matrix shear stress, and then the fiber diameter. And if you plug in nominal values for these, you get a critical length on the order of a millimeter. So we're not talking about needing huge lengths of fiber in order to develop this bond. But if you have really tiny fibers, it's going to act more like a particle than a fiber, right? Which kind of makes sense because its size and shape is more like a particle than a fiber. So length is important, and right, also alignment here. So if you have long fibers that are aligned parallel with the direction of desired strength, right, then you're going to have a stronger material, at least in that direction. And if you have short fibers, aligned is going to be more effective than a random. So with fiber direction, right, you have fiber length. You also have alignment, and then the direction of that alignment. Okay. Yeah, as I mentioned before, orientation is important. And within a polymer reinforced or fiber reinforced composite, there are two main conditions that you can be under, right? Isostrain and isostress. Now, the prefix iso means the same, kind of like isotropic properties means the same in all directions. So isostrain means that the matrix and the fiber are under the same strain. And so they are being elongated together, which means that there's a good bond, right? So if they're not bonded together, then they're not going to elongate together. They're not going to deform together. And we see here that in this stress-strain curve, right, you can see the individual responses of the components of the composite, and then the response of the composite itself. And like you'd expect from the rule of mixtures that we showed before with the upper and lower bound, right, that the properties you get with the composite, right, fall somewhere in between. And in this isostrain condition, right, you have them pulling together, but at some point, right, as you increase the strain, you're going to yield one of the components, right? So if you reach the maximum strain, say, for the matrix first, then what happens is the matrix starts to yield. And as it yields, the load is shifted to the fibers, and the fibers carry more of that load. So you can see here that what happens at this point when the matrix is yielding is what you may expect is that if the load is transferred to the fibers predominantly, then you should see a shift in the modulus, which you do. Okay. And then and so here you kind of see this rule of mixtures. You can define it in terms of the volume fraction for the matrix and the fibers independently, or with the recognition that they both add up to 1. You could define it in terms of just the volume fraction of the fibers. But this is you have a combination because they're pooling together in an isostrained condition that this rule of mixtures is more of the upper bound, right? That would be sort of the ideal. And is indicative of longitudinal loading. So that would be this picture here where you're pulling in the same direction that the fibers are aligned. In an isostress condition, right, this would be where you're actually pulling in the other direction. So you're kind of pulling in the transverse direction, which is anti-alignment, aligned with the fiber direction. And this is kind of the lower bound or the worst case scenario because every component is under the same stress, right? So if I have matrix next to fiber, next to matrix, next to fiber, and I pull on the matrix, right? Then I'm pulling, all of that strain is going through the matrix to get to the fiber, and then going through that fiber to get to the neighboring matrix, and so on and so forth. And so I have equal stress to all components, so they're not really pulling together; they are pulling separately. And it's not really, acting as a composite material. It's kind of acting as a collection of different regions of different materials. And so this would be kind of the lower bound or kind of the worst case scenario. And so the form here for this equation should look familiar from what we talked about before. And this is indicative of fiber reinforced composites in that they are highly anisotropic, right? Which means that their properties differ in different directions, specifically longitudinal versus transverse loading. For these three commonly encountered composites, you see that you're talking about a factor of let's see, 50 times stronger in the longitudinal direction than in the transverse direction. And so when you're building your part, right, the direction that you orient your fibers and the load path through that part is important to understand, right? You want to align your fibers in the direction that it needs to be strong. Okay, so if you can't get long continuous fibers, you could at least align them. So this discontinuous would be shorter fibers, and you see here have this composite property here. And I'm actually going to look over at my textbook because I forget off the top of my head what some of these variables in this equation are. So here we have the case for the combined longitudinal strength for two cases. One where the fiber length is greater than the critical fiber length, and the other where it is less than. And I'll point out, right, so here we have the fracture strength of the fibers in the matrix, which that makes sense, right? You're going to have a combination of the properties of the components individually. And then you see here that there's this factor that modifies the contribution from the fiber. And as the fiber length is increased, right, this quantity here decreases, right, which is this ratio is subtracted from 1, and so we see that the longer the fiber is, the higher the composite longitudinal strength is, and the greater contribution the fiber makes to the overall strength of the material, which makes sense. If you look at this case where the critical length or the length of the fiber is less than the critical length, you see a similar contribution from the matrix. And here, there's no enhancement. There's really no, the shear or the fracture strength of the fiber is not even in this equation at all. Instead, you're looking at tau sub c, which is either the fiber matrix bond strength or the matrix shear yield strength, right? So this portion of the fracture strength for the composite, right, is driven by the bond or the matrix material. And even so, even though you're less than the critical length, you still see an enhancement when at least your length is longer than your diameter. right? So you may not be at the critical length, but as long as you have, if you can increase the ratio even below this threshold, right, you're still going to get an enhancement. So even when you have short fibers, right, even like a little bit longer is going to help you out. And then, of course, if you have discontinuous fibers and they're randomly oriented, right, the random orientation is going to give you isotropic properties. You only get anisotropic when you have a difference between the different directions. And if it's randomly oriented, you're going to have some that are aligned in a direction, some that are aligned in another direction, and overall it's going to kind of average out. And so here, where you have the rule of mixtures, you are going to have the contribution of fibers and matrices a bit separately. Whatever role that you would get of, say, load sharing between adjacent fibers, even if they're randomly distributed, is kind of rolled up in this K factor, which modifies the contribution of the volume fraction of fibers accordingly. Okay. So I think this is a typo. I've already talked about fiber length quite a bit. I think this should be fiber width, actually. And in this case, thinner fibers tend to give you better properties. And that is because the fibers tend to be ceramic materials. And when you have a ceramic material, if we recall, right, the tensile strength is dependent upon the sample size. And that's just because the larger your sample is, the higher your probability that somewhere in that sample you'll have a critical flaw of a critical size, which will lead to a crack and failure of your specimen. So if you have a smaller specimen, there's less likely that you'll have that critical flaw. And so we see here that, for whiskers, which are very thin, much thinner than fibers, which themselves are much thinner than wires, right, that we have in a whisker much better properties because, we're more likely to have a perfect single crystal than we would in a much bigger wire. And, for, really high-performing, material samples, kind of like reaching theoretical strengths, right? It is for these really small whiskers or nanoparticles. For fiber-reinforced composites, the matrix material can be pretty much any type of material, a metal, a polymer, or a ceramic. The most common, at least from what I've seen, is to have polymer matrix. But in all cases, the matrix material is there to bind the fibers together, to transfer load from one fiber to the next, to protect the fibers from environmental degradation, and to slow the crack propagation, right? You may have a crack in any one fiber, but if it needs to move through the matrix material, then that is going to slow that crack propagation and increase the fracture toughness of that composite material. In all cases, right, we're dependent upon good bonding with the fibers, right? If we don't have a good interface, then none of this, or less of this, these properties will happen, especially this crack propagation and load transfer. If we don't have a good bond, that's not going to happen as effectively. Looking at these individually, probably the more common, at least by weight, is polymer matrix composites. And you can have different fibers. You can have glass fibers. This is like fiberglass composites. These are prevalent in marine applications. They're relatively cheap to make, and so they are more common in recreational and industrial use. If you need a stronger material yet, you can swap out the glass fibers for carbon fibers. These are more thermally resistant and stronger. They're also more expensive. And the carbon fibers themselves can have a range of mechanical properties depending upon the particular heat treatment and the degree of crystallinity that that the graphite and the carbon fiber has achieved. You can also have aramid fibers. This would be like Kevlar or Nomex. And in these fibers, during the manufacture, right, the molecules, the polymer molecules are aligned, which gives you, right, this is the drawing that we talked about last lecture, which gives you strength in the fiber direction. Polymer matrix composites, probably the Achilles heel here is that generally the matrix, since it's a polymer, is the limiting factor for the temperature range that these materials can be used in. The matrix material really limits the application in this way, right? So the glass transition temperature of common polymer matrix materials like polyester or epoxies is going to be in the range of say 100 to 150, and then the decomposition temperature is about 300 C or so. And so it really limits the application for polymer matrix composites. You can also have a metal matrix composite. So here you're generally talking about non-ferrous alloys as the matrix. This would be due to the fact that these have a much lower melting point, and which is necessary if you're going to form a melt and add in your reinforcements. Like we saw in the examples before, the reinforcements tend to take the form of particles, fibers, or whiskers of ceramic materials with a higher melting point, obviously, so that they don't melt themselves during the making of the material. So we're talking about carbon or various carbides or boron or alumina, right? All ceramic materials. Having a metal matrix gives you the ability to go to higher operating temperatures. You also have a non-flammable, right? The other thing is that the polymer matrix materials, right, if you were to go above their working temperature ranges, when they decompose, right, they form flammable byproducts. And so using a metal matrix composite can give you a measure of weight reduction or abrasion, right? You can have hard particles to keep it from being abraded, and dimensional stability. So you would have less of, thermal changes. Composites do tend to be expensive. If you think, you have much more processing that goes into it. You have to prepare the reinforcement, you have to add them together, and these are generally lower volume, right, which drives up the unit cost of these parts. For a ceramic matrix, it's a similar idea where you have a ceramic reinforcements. This time you're just putting in a ceramic material instead of a metal matrix. And doing this is the primary benefit is an increase in fracture toughness, right? So if we recall, ceramic materials are strong and they're hard, and their Achilles heel is that they don't deform, which means if a crack forms, it propagates very rapidly. And so the reinforcements are there primarily to impede the crack propagation. And one of the ways it does that is through a process called transformation hardening, where you actually have the particles, the reinforcing particles, are able to, they have two phases, right? So, if you look at their phase diagram, they, as a function of pressure and temperature, right, you've got regions of these two phases, and what happens is you have the particles in the material normally in one phase, and as a crack is propagating, it is putting these particles under compressive stress. And this shifts, right, the point in the phase diagram, and if it shifts it into a region where there's a phase change, right, that compressive stress can actually initiate a phase change in these particles. And if it changes crystal structures, like in the example here with these zinc oxide particles changing from tetragonal to monoclinic, right? A change in crystal structure comes with a change in volume. And if the volume increases, right, then you can actually exert from within the material itself a compressive stress at the crack tip, right? Which, as we've seen several times now, can impede that crack growth, right? It tends to push it closed rather than pulling it open and making it longer. You also might have the instance where you would have a whisker or a fiber that actually spans the crack, right? And so for the crack to propagate, it's going to have to either break the bond or break the fiber, right? And breaking either takes energy. And so similar to deformation of a metal at a propagating crack tip, absorbing energy, right? Breaking this bridge does the same thing. Ceramic matrix, so processing was a difficult thing with ceramic materials in general, and we have a similar way here of creating this where you would have a hot pressing or sintering where you have a collection of these particles, and the matrix itself would be maybe particles you mix together two different kinds of particles, and then you hot press or you sinter, and you end up with a solid material. All right, last page. What am I doing on time? 46. Okay, not too bad. The last two examples of composites, we have carbon-carbon composites. So carbon-carbon, if you've not heard of it, these are meant for high-temperature environments, generally, where you need to have strength at high temperatures. So these were used on the space shuttle for the leading edges. And they have, that doesn't make sense. How can it be low and high thermal expansion? I'm going to have to go back and figure out what I meant to say there. I'm going to, yeah, that's curious. Also, well, they either have, I think, probably low thermal expansion. They also have, there might be high thermal resistance. They also resist creep and have high fracture toughness. And carbon-carbon composites are made, similarly to polymer matrix composites, in the sense that you have carbon fibers in a polymer matrix, but there's an additional processing where you intentionally heat up and decompose the polymer matrix through a process called pyrolization or pyrolysis, and you drive off some of the organic components, leaving a porous carbon matrix, and then that can be later backfilled with more polymer and the process repeated, and along the way, right, you are creating a composite where you have a carbon fiber in a carbon matrix, and so this, since you basically have already broken down and pyrolyzed the polymer matrix, right, gives you high temperature resistance. But again, right, this is a lot more processing, which drives up the cost of this material. You may also, for various reasons, have a need for a hybrid composite. So this might be, it's essentially a composite of composites where you would have two different composite materials combined together. An example might be having a hybrid material of glass and carbon fibers, where you get a little bit of the benefit of the carbon fibers in a glass fiberglass composite, but not at the same cost of a fully carbon fiber composite. The processing here is more simple for the fiber reinforced polymers or fiber reinforced composites. You need to somehow get the fibers and the matrix material combined, and that kind of depends upon the form factor for your resulting part, right? If your part is, say, a rod or a channel or something, you may be able to combine the fibers and essentially kind of have like a extrusion type die where you have this continuous piece that's being pulled out. I would say more commonly, you don't know what the form of your final part will be, or it's not something with a consistent cross section, and so you would instead spool your fibers into a sheet and combine it with the polymer matrix material ahead of time, right? And so this material is called prepreg, and that's kind of a partially cured polymer matrix with the fibers included, and this is handy for laying up parts individually or in small batches. You essentially just have layers of this material that you can orient and layer multiple layers together to create your part. You just lay them into a mold. Then you would typically put a vacuum bag in there and then take the whole thing and throw it in an autoclave. So the mold will shape the part and then it will cure in place. If you have an application, say compressed gas tank or something, right, you may find yourself wanting to winding the fibers either around, in various patterns, as shown here, around the form to form that tank, and then impregnating with resin and curing. Okay, the last topic here are structural composites. So when you are taking especially these fiber reinforced polymer composites and making a part out of them, especially for a wing skin, it's common that you will not have a continuous piece of the composite material, but instead you'll put it right where it's needed most. In this case, you would have these laminar composites here. And the laminar is, you have various laminates, so you would have fibers running in alternating directions, which gives this, quasi-isotropic properties, at least in this plane. And you may take two laminates here and put them on either side of a honeycomb panel. And so combining composites structurally in this manner is one way of getting a high degree of stiffness in a very light package. So again, composite materials is an effort to combine different classes of materials intelligently to end up with a material that has the best of both worlds, right? Or at least a combination of properties that you couldn't get inherently in any one material system or material class.